But you just have to get through the whole something really good happens.
Okay, so welcome to the next installment of our Lunch and Learn lecture series. So in general, during the fall, what we like to do is to cover some more of the basics. So this is the fourth year in a row that in September we've done an introduction to light microscopy talk. But I'm happy to say I'm also the fourth different person to do it. So it means that the talk has never been the same. So just before we get started, this is really just kind of scratching the surface. And we're going to do some real basic stuff. But just before we get started, I want to tell you, if you want to dig a little deeper and want to find out a little bit more about this, here are some other resources. So this course right here at MCB 352, this is a course that Jeff Lichtman and I teach. It's usually held in January every year. It's 2 days, introduction to microscopy, and it's either 4 or 5 hours of lecture each day. I forget, it's intense. But it covers everything. So I'm going to try and do a small portion of that today in 1 hour, so you can get an idea of how brief this is going to be. But that's a really great course. Jeff does most of the teaching. I just do a couple of small sections at the end, and he's phenomenal at explaining this. There's another similar one that I help with DRB 330. This is another one of the nano courses or boot camps in January. We spend 1 day doing microscopy in that. Similar Micro 302, another boot camp in January. And then MCB 68, it's an undergrad course. It's next term. But I know I put it up there as an undergrad course, but I know a lot of the people who have acted as TFs and TAs for it have really gotten a lot out of it. They've learned just as much as the students. And it's actually been awesome to see those people come back into the facility and TF or TA for it and apply what they learned in the course in the facility as well. So there's a couple good textbooks out there. This one by Murphy and Davidson came out a couple years ago, and it's a really great textbook. It goes in conjunction with Mike Davidson's website. Like you've probably seen, he has this, it's called Molecular Expression website, which has now been picked up by all the major manufacturers. So if you go to Zeiss, Nikon, and Olympus, they're all using Mike's sort of slides and images. This one's a little more complex and more specific to confocal microscopy. This is James Hawley's famous textbook. And so it's really thick, really good, lots of information there. And then if you just rather watch some videos, the iBio microscopy, so the iBio website, they now have a microscopy section in it. So Jeff Lichtman actually has a couple of great lectures on there, and a ton of people from the world of microscopy. And of course, all of the lectures that we're doing here now, we're also trying to post those on the HCBI website. So if you want to watch this again. Okay, so what I'm going to do is try and talk about these two things today. I think these are the most important things to really get the basics of a light microscope. So the first section is just going to be image formation and magnification. And we're going to start by looking at some really simple systems and build up to what actually happens in a modern microscope. And then we're going to talk about the resolution limit of microscopes as well. So this is something that's really important to keep in mind when doing light microscopy. There's really two aspects to this. One is the actual laws of physics that determine what type of resolution you can get out of your microscope. But there's also a lot of important things that we sometimes don't think about that we can do on our end to affect whether or not we've reached that level of resolution. And that has to do with sampling rates and pixel sizes. Okay. So that's what we're going to try and get through today. So what I want to do is just start by looking at some really basic systems. So what I've tried to diagram here is what's called a pinhole camera. I don't know if anyone's ever seen one of these. It's kind of the most simple, basic imaging system you can think of. Basically, all it is a cardboard box with a little hole inside of it, and then inside of that cardboard box, we put a piece of film. Right. And what you do is you have some sort of cover over the pinhole, you open that up for some sort of exposure, and then cover it again, take your film out and develop it. And you'll see an image there. So what's happening in this system. So let's take a look at this object. Let's just have it as an arrow. But you can think of it even as just one person standing in the middle of this room. Right? That object or the person standing in the middle of the room, they aren't a luminous object. They're not creating light, right? They're not a light bulb or anything like that. So where's the light coming from? Everywhere, right? It's coming from all the lights around the room here. If you got the shades open, there's light coming in from the windows. So that window, all that light is coming in from many different directions, hitting this object, and then what it's going to do is going to bounce off, right? Okay. And it's going to bounce off in all directions. So if we just look at the very, very tip of this object, and we want to see where that tip shows up on our film, how do we trace that out? Kind of gave it away by saying the word trace. We're basically going to draw a line to our film, right? But there's a lot of different lines that we could draw. All right? But here's the magic of the pinhole camera. All of these other lines that we've drawn here just hit our cardboard box and don't get through to our film. Okay? The only one that's going to make it through is the one that goes from that tip straight through that pinhole onto the film. All right? So if you want to call it a ray, we've got this ray of light going from the tip landing down here on our film. So that's where the top of the arrow lands. We can do the same thing for the bottom of the arrow. There's only a specific path that they can travel to get through this hole and get to the screen. And now we have our object that's been projected onto this film. Okay? Now, what would we do if we wanted to magnify this object and make it bigger? Two things that we can do.
Put the film further away.
Sorry?
Put the film further away.
Put the film further away, exactly. That's the one that I didn't anticipate. What's the other thing that we could do? What about the object? Yeah, we can move the object closer. Okay? So if we move the object a little bit closer, we do the same thing, just trace the top and the bottom. You can see now we have a larger object. Okay. So this is the most simple imaging system that I can think of. And the way you get magnification is by moving your object closer or moving your film further away from that. So let's make it a little bit more complicated. What we're going to do now is we're going to introduce a lens. Okay? So in microscopy, we're usually always working with convex lenses. And convex lenses are able to focus light. And they do this by refraction. So hopefully we're all familiar with this idea of refraction, that light travels at different speeds in different substances. And you can give something a refractive index. So it's a number that indicates how fast light moves through that substance. So it's defined by this equation, your refractive index, which is n, equals the speed of light in vacuum divided by the speed of light in your particular material. So the reason this focuses light is this ray traveling through the middle of the lens here, it has to go through a really big piece of glass, okay, relative to a ray traveling at the top there. And light moves more slowly through glass. So what we're going to have is this ray is going to get slowed down. It's going to get slowed down for a longer or a greater duration of time than the ray going through the very top here. Okay? But to get to the focal point from the edge of the lens here, this ray has a shorter path than this one that has to come down from the top. So what that means is when you sort of add up how much this ray slows down going through the middle versus how much further this one has to go, everything ends up landing right at this point. Right? And this is the idea of refraction, and this is how we focus light with convex lens. So across the bottom here, this is a total aside. This has pretty much nothing to do with anything else we're going to talk about today. But this is just an example of some of the different refractive indices that are really important in microscopy. And what you'll probably notice is these air, water, glycerol, and this is glass or oil. You can see these are all types of immersion media that we use in microscopy, and as well as labs, is what our objectives and our coverage slips are being done. So those are important numbers that you usually want to keep in the back of your head and know when you're dealing with microscopy, because they come up in various different points. Okay, so how do we do a tracing of an array diagram when we're dealing with a lens instead of that pinhole camera? So the pinhole camera was really easy, but you probably remember this, or maybe you don't, from high school or maybe first year in undergrad. There's essentially 3 rules to this. So we have our object here, and we have our lens, and then we have the image of our object on this side of the lens. And there's 3 rules here. So any incident ray which is parallel to the optical axis, so this is the optical axis here, the dotted line. This is our incident ray that's parallel to it. It's going to be refracted through the focal point of the lens on the other side, okay? So it comes in parallel, refracts through the focal point, that's a little red dot here, one on both sides. And so we draw that ray, okay? I'm actually going to scoop to the third one here. Any incident ray which passes through the optical center of the lens is not refracted at all. So that's this guy here, which goes through the center of the lens, bottom. Doesn't refract at all. And any ray which passes through the optical center of the lens, any incident ray which passes through the object focus of the lens is refracted parallel to the optical axis. So that's this guy here. It goes through the focal point on this side of the lens, and it gets refracted parallel to the optical axis. Okay? And the point where these 3 rays meet, that's where your object is imaged. Okay? So these are the 3 rules that we have to keep in mind when we're drawing these ray tracing diagrams. So now if we have one of these convex lenses, you can see this object right here is sitting at 2 times the focal length. Okay? So 2 times the focal length. And you can see the image is exactly the same size. So how would we make the image bigger in this situation? So here we really only have 2 things we can move, our object or our lens, because this is just an image over here. So what would we do? Yeah, so we're going to move that object a little bit closer. And what you can see, so we've moved this just a little bit because I didn't want to draw a bigger lens. And what you see here is if we do our 3 ray traces, our image is now a little bit bigger. All right? Now what happens if we move that object inside of the focal point? Okay? So what I'm going to do is I'm going to try and draw those 3 rays again. Okay? So our first ray goes parallel to the optical axis, and then goes down through the focal point. Our second one is going to go through the optical center of the lens and not be refracted. And then our third one, we can't really draw because it's going to go back this way, right? So what happens here now? We have 2 rays that are actually diverging from one another. They're getting further and further away from each other. So where is our image point? So what we have here is a situation where we don't have what's known as a real image form. We have a virtual image form. And what we're actually going to do is we're still looking for the place where these 2 rays intersect. But instead of being on this side of the lens, those 2 intersect back over here, right? So if I extend those back this way, we get an intersection up here. And now you can see our object is dramatically magnified compared to the original. So So there is an imaging device that I guarantee all of you have probably used at some point in your life, but works this way. Any idea what it is? It's a magnifying glass. Okay. So your eyeball sits down here, where the magnifying glass is. And what you actually see is an interpolation of the way your brain looks at this and configures it. It feels that this object is actually sitting on the other side, on the same side as your object is. The image is sitting on that same side. Okay. Cool. So that's what happens, how we get magnification when we have things close to our magnifying glass or our lens. So what happens if we have something that's really far away from our convex lens? So if we just draw our same three rays here, so we have our one that's coming parallel and it gets retracted to the focal point. We have the one that's right to the opposite center, doesn't retract. Other one that goes to the focal point on this side, and then goes parallel. You can see we have an image on this side that is reduced in size, so it's smaller. But that's not what we're trying to do today, right? We're trying to make things bigger. So how would we go about making this bigger? The answer is a combination of things that we've already learned. So what we can do is leave this imaging system intact, add another lens where our image here is now inside of the focal point of this lens. So I just put this focal point is exactly the same for this lens. Now we have the same situation that I just showed you with the magnifying glass, where we've got rays that are diverging, but we can trace those back to make a virtual image here. All right? Now this is just slightly larger than this. Had I done a better job of drawing this, I can show you how you can actually magnify this quite dramatically. But any idea what type of imaging system works this way? So something that's trying to magnify an object that's a long way away from you.
Telescope.
Telescope, exactly. Okay. So this is what's going on inside a telescope. You've got an objective lens, which is this guy right here. Which actually forms a smaller image. And then you have another lens in the eyepiece here, which works just like a magnifying glass to magnify it. In a very simple way. All right. So what I've done here is I've shown you three very simple examples of how to get magnification. So we looked at the pinhole camera that doesn't even use a lens. We looked at a magnifying glass that just has a single lens. We looked at a telescope, which has two lenses. Any idea which one of these is what's going on inside your microscope? It's a trick question. None of these are going on inside. At least not in your modern day microscope. So a modern microscope works with what's called infinity corrected optics. Okay? So what this means is when you have your sample sitting on your microscope, any microscope in our facility is a fixed stage microscope, so the stage doesn't move. But you have your objective moving up and down, that's how you focus through your sample. But then all of the other lenses that are in the microscope, they don't move, right? So how is it that that objective is able to move without throwing off the rest of your optical system? And this was this really cool development called infinity corrected optics that came out a few years ago. Not a few years ago, quite a while ago. So the idea here is that instead of our object sitting far away from our focal point or inside our focal point, it sits right on the focal point. Okay? And so if we do our ray drawings again, what's this going to do? So we've got our first ray that comes parallel, reflects through the focal point, and comes down here. Our next one goes straight through the center, optical center of the lens. And our last one is useless because it's just going straight down. So what do you notice about these two rays here? Are they converging or diverging? They're parallel, right? So this is the really interesting thing about a microscope objective. As long as your sample, or the object that you're imaging, is sitting right at the focal point where it has to be for it to come into focus in the microscope, the light coming out of the back of your objective is actually just a whole bunch of parallel rays that you would never be able to image it. Okay? But what's interesting about those parallel rays is that the angle that those rays are on are actually encoding something. They're encoding the position that that light is sitting at in your sample. So here's our sample sitting here on this white line, and we've got 3 objects on it. So you can think of it as, say, 3 fluorescent beads. And the light coming from the bead in the middle is just traveling straight through the objective. Whereas the light coming from this green one at the top goes through our objective and comes out in an angle in this direction. And the yellow one here comes out in an angle in this direction. And the other thing that you have to think about too is I'm just showing you kind of 2D cut-throughs of this. But this is actually happening in 3 dimensions as well. So these angles are not just up and down, but they're also coming in and out of the plane of the screen here as well. So this is what an objective does, is it actually takes the light that's coming from your sample and encodes that in a whole bunch of different angles at the back focal point of the objective. So again, I said I'm going to try and keep everything somewhat simple today. So what I've actually done is I've cut the traditional microscope like half and half. I'm not talking about the condenser and the light source or anything like that today. Okay? And one reason for that as well is most of what we do is fluorescence microscopy, so we're usually not using condensers. Our actual objective functions as a condenser as well. So what we have here is our sample sitting at the bottom, our objective, a bunch of parallel rays coming out of there that are encoding our position in our sample. And then we have what's called the tube lens. So this is a tube. This tube lens takes these parallel rays and then reconverts them into positions again. Okay? So this is an image plane here where all these converge. And then if you're looking through the ocular or the eyepiece on the microscope, you have an additional lens that converts that positional information back into parallel rays again. And then we have a lens in our eye that takes those parallel rays and converts them back into positions at the back of the retina. Okay? So what you're doing is you're going from positional information in your sample to angle information behind the objective, to position information behind the tube lens, to angle information behind the eyepiece, to positional information on your retina. Okay? And what's neat about this is this area right in here is what's called infinity space. And that means this objective can move up and down and not affect anything in here. To some degree, obviously if you move it too far, you erase this too much. This also means we can stick a whole bunch of things in here. We can stick in fluorescent filters, we can stick in polarizers, things like that into the light path that aren't going to affect anything. Okay? So this is the magic of infinity-directed optics. But that still leaves the question is how do we actually get magnification? So in an infinity-corrected system, if you draw these somewhat more complicated ray diagrams, what you see is that it's the working distance of your objective that determines your magnification. Right? So in the bottom half here, we have the low magnification system. So you can see here's our object and here's our image. It's been magnified a little bit, not a lot compared to this one. And what you have here is a really long focal distance for this objective. Okay? And you can see that focal distance is the same on this side of the objective as it is over here. And then if you ray trace this back, you get a minimal magnification. if you shorten this radius for your focal distance, so you can see this is here, shortening this distance here. Same thing, your back focal plane now moves a little bit closer to the objective lens. And if you ray trace this through, you then get a greater level of magnification. So this is why when you're looking on the microscope, you use a 10x objective. That 10x objective is nowhere near your sample. As soon as you move to a 63x objective, that objective is right there, almost touching your sample. Okay? What this also means is that if you have a big, thick sample, say it's like 500 microns or a millimeter in thickness, you can't move all the way through that with your high magnification objective, because it only has a couple hundred microns of working distance before it actually runs into your sample. So that's the idea of how magnification works within a light microscope. So I'm just going to quickly talk to you about a few things that affect image quality. And Sebastian talked a little bit about these as well during his talk on objectives earlier this summer. So I won't spend too much time on them. But these are things that can affect our imaging. So chromatic aberration, spherical aberration, flatness of field, and diffraction. So this is an image of some fluorescent beads that I took on our Lyra microscope. So this is in super resolution structured illumination mode with like a $15,000 to $20,000 objective, so one of the best objectives you can possibly buy. And what each one of these beads is it's called a tetraspec bead. So it's a little latex bead that has 4 different dyes inside of it. So I've just imaged blue, red, and green here. And all of those, the light of those 3 different colors should be coming from the exact same place, because it's all evenly mixed through that bead. And so if we take a look up here, you can see some of these beads look whitish, which is what they should be if the green, red, and blue are all aligned on top of each other. But if you blow up some of these, you see you actually have this little spread. So this is actually one single bead, but you can see our light is spreading out here. And this is actually even worse in the axial dimension. So this is looking at Z, and you can see here's our blue, here's our red, here's our green. So this is what's called chromatic aberration. Okay? The software has a nice way to correct for this. So you can see once you do this post-alignment, all of these beads now become yellowish white, and everything gets realigned with blue. But this has always been a well-known problem with objective lenses or any lens. And the reason for this is blue light refracts more than red light. So what you see is your blue light getting focused before the green and before the red behind your lens. So this was fixed a long time ago by a scientist known as Joseph Lister. And what he realized was that you could take 2 types of glass that had slightly different refractive indices, and you could actually correct for these. So you made a convex lens with your crown glass and then a concave lens with your flint glass. And due to the different refraction that you get in these 2 substances, you're able to actually get these to land at the same point. But as I showed you before, it's still not quite perfect. Another issue that we often have is spherical aberration, which in general just looks like blurriness in our image. And what's happening here is, in a perfect lens, you would have every ray of light, no matter where it hits your lens, it would get focused to the same focal point. But with spherical aberration, what happens is sometimes your lens isn't quite perfect, and the rays that are hitting the outside don't quite get focused to the same focal point as the ones hitting more towards the middle. And this is when you get spherical aberration. The other thing that you can often run into is flatness of field. So if you look at the objective lens in your microscope, what you see is it's actually, the front lens is actually usually concave. And obviously within your objective you have a whole lot of components. But what that means is you're mapping your flat sample onto a curved surface of glass. And so you can also get this distortion when it's actually kind of curving your sample on your image. So spherical aberration and flatness of field are corrected by putting essentially more and more lenses into that objective. All right? And there's a certain nomenclature for this, so anything that's plan on it should be corrected for flatness of field, and anything that says a chromat should be corrected for some amount of chromatic aberration. Usually what you're looking is for one of these plan control people chromat. Then what you're getting is spherical aberration across 3 or 4 colors, chromatic aberration across 4 or 5 colors, and a nice flat field. Right? So these are pretty much all we have on the microscope. So there's a couple of exceptions, but for the most part, everything else there is a equal. Okay, so for the last little while, what I want to talk about is resolution of the light microscope. And like I said in the introduction, this comes from, this resolution limit comes from 2 places. One is just due to physics, so the nature of light moving through objectives. But the other one is actually something that you can control, and that's due to sampling. So if we go back to this really simple example that we had of the pinhole camera. What happens to our image if we make that pinhole bigger? It gets blurry, exactly. So now, instead of just getting that single ray coming off the top here, we're collecting a whole bunch of different rays that are coming through and getting onto our phone. And that's going to make it really blurry. Okay. So what happens if I make that a little bit smaller, it gets sharper. What happens if I keep making it smaller and smaller? Does it keep getting sharper and sharper? Until at some point it's not a hole anymore, we don't get any light through. All right. So that's that's the answer if light just traveled as rays and traveled as particles. But we know light is actually a little bit more than that. So we've probably all done these experiments back where you have these little light boxes with these little slots. So you went through a lens and then you could watch, you could trace your rays and measure your angles and everything like that. And so in early high school, elementary school, we always described light as being a ray, moving as a particle. But the truth is that it's not. It has this weird duality in that it's partially a particle, a ray, and it's also partially a wave. So this was a really neat experiment, but again, it was done way back in the 1800s. And here what Young did was he took some sunlight, let it pass through a little narrow slit, and then projected that light onto 2 more narrow slits. And then what he had down here was a little screen. So this is just a screen, and then this box down here is showing you what he actually looked for on the screen. Okay? So if he only opened the slit on the right-hand side and looked at the screen, you just saw a nice broad swath of light, which is what he expected. If he does it on the left-hand side, sees exactly the same thing, just shifted a little bit left. But what happens when he opens both slits at the same time? So if Newton was right and light was a particle, and was moving like a ray, what you'd see is basically an overlay of these two. Okay, so it'd be bright in the middle and get a little bit dimmer closer to the edges. But that's not what Young saw. What he actually saw was this bright spot in the middle, and then a whole bunch of little fringes, little lines around the outside. And this was the initial indication that light actually has properties of a wave as well. So when we were talking earlier about if there's an object in the middle of the room here and the light is coming in and hitting it, that light bounces off in what we call a spherical wave. So you can think of this as dropping a pebble into a pond and the rings that come out from it. Okay? And if you look at that spherical wave, the further and further you get away from where it began, it looks more and more like a plane wave. So just a straight line. So what you can do is if you take a plane wave that's coming in and you have one little slit, you actually then get diffraction, which leads to, it turns that plane wave into a spherical wave again. Okay? And so that's if just the left slit's open. If you have just the right slit, you have the same thing, just shift it a little bit. But if you have both of these slits open, you now have these two new spherical waves of light. And what you do is you actually get some interference between those. So constructive interference and destructive interference. And that's what you're seeing here. So wherever you have white, you have constructive interference where both of these waves are adding to each other. And wherever you have a black line, you've got destructive interference where they're interfering with each other. So essentially what lenses do is they take plane waves and turn them into spherical waves, or vice versa if the light's moving the other way. So another way to think of our microscope is instead of looking at position and angle, we can say, okay, coming off our sample here, we have a bunch of spherical diverging waves. But then once they pass through our objective, become planar parallel waves, so plane waves. Go through our tube lens, they become spherical converging waves again, and then spherical diverging waves. And then after the eyepiece, they're plane waves again. And then finally after our eye, they become spherical waves. And this is essentially what determines the resolution of our microscope, is the degree to which we get this interference pattern behind our objective. Right? So the one way to think of this is that as your light comes in, it's actually a whole bunch of these little tiny wavelets let hit the lens. And so if we just have 3 wavelets, so this is kind of like doing a triple slit experiment. So here's our tube lens. This is what's happening behind our tube lens, where we're taking plane waves, converting them into spherical converging waves. And those spherical converging waves are all interfering with one another. So if we have 3 of these coming in, you can see this pattern gets a little more complex. And there's also one difference here between what I was showing you before. This here is just a snapshot in time. What's happening here is this is an aggregate of a whole bunch of time points. Okay, so what we see is here's where our primary imaging plane is. You can think of this as where your camera chip is setting. And if we just had 3 little waves, we see a diffraction pattern that's still fairly similar to what Young saw with the double slit experiment. But we don't have just 3 little waves hitting on the back of our tube lens. We have many. So you can see if we go to 5 along here, you can see now we sort of have 3 bands that are becoming a little more predominant, and the one in the middle here is the brightest. And now the closer and closer you get to an infinite amount of these little wavelets that are hitting, which is really what's going on inside behind your tube lens, you can see that this really ends up with a whole bunch of constructive interference right in the middle here, and a lot of deconstructive interference on the inside. So if you look at your camera chip right here, what you're seeing is this bright spot in the middle. And here we've just played with the contrast so that you can see this a little bit better. And you can see there are still some fringes along here, but they have a much lower intensity than the middle band. Any idea what this looks like? Does anyone recognize that pattern? So you probably recognize it more if I show you this one. This is what we call a PSF, or point spread function. So this is if you had an infinitely small point of light in your microscope. Once it passed through all of the optics and diffracted and got to your camera, it looks like this blurry spot with a bunch of rings around it. That's what it looks like in the XY dimension, and here's what it looks like in the axial dimension. And so you can see this looks exactly like this. Okay. So what determines the size of this blurry spot here, or this point spread function? And it's mainly determined by the distance between the most extreme pair of wavelets. So the wavelets that come at the edges here. And the other thing that's important too is the frequency of light, okay, or the wavelength. So Sebastian spoke about this during his history of microscopy talk a little while ago. Ernst Abbe, who I discovered I pronounced his name very correctly, thanks to Sebastian. So back in 1873, he came up with this equation that essentially says what I just told you. So the minimal distance between two objects that you can resolve in a microscope, so the resolution limit of your microscope, is equal to the wavelength of light divided by 2 times the numerical aperture of that objective. So the numerical aperture is just the distance between the outermost wavelets that enter that objective, and then lambda is frequency of the wavelength of light. Okay. So just to give you a quick example of what this means. So here we have 40x air objective. You can see that as a numerical aperture of 0.75. It's an air objective, so if we plug everything into his equation here, let's just look at some green light. So we have 550 nanometer light over 2 times 0.75 or numerical aperture. We get a resolution of about 400 nanometers. Okay. What we can do is we can leave the wavelength of light exactly the same, so we'll still deal with green light. But we're going to go to an oil immersion objective, which has a higher numerical aperture, 1.3. So this means we can collect light from wavelets that are more extreme at the edges. And now what you see if you plug those numbers in, we go down to a resolution around 200 nanometers. We can take this one step further and change the wavelength of light that we're looking at. So instead of looking at green light, let's look at near UV light. And now what we have is a resolution limit down near 170 nanometers. Right? Now in general, the number that you always hear as a resolution limit of a light microscope is 250 nanometers. This is kind of a bit of an average, assuming that you're using green light and numerical aperture around 1.2, 1.3. But obviously this number varies dramatically depending on what type of projector you're using and what color of light you're using. So just to reinforce what numerical aperture means, so I said it's the outermost extreme wavelets that you can accept into your objective. A better way to think of it is the cone of light that's entering your objective. So in this situation, we have a sample here, a slide. We've got our sample. We have a cover slip on top of it. And we've got some light coming from the point in the middle of our sample here. Now, this is a non-immersion objective. It's an air objective. So what we have is just air in here with a refractive index around 1. And so what that means is we have a big refractive index mismatch here between our cover slip that has refractive index around 1.5 and our air. So what that means is some of the light that's coming out of our sample, you have a molecule of GFP here, it's letting photons out in every possible angle. So what that means is some of them are going to come at an angle where you have what's called total internal reflection. So because of this refractive index mismatch, it just bounces back down into the glass. We've got some that are going to be refracted so much that they miss the objective. And then we've got some light from there that's going to go up into our objective, can interfere with itself inside that objective and give us some decent resolution. But if we want to improve this, the easiest way to do this is to just stick something in the middle here, like oil. So now we've got some immersion media, some immersion oil here. And now what you can see is this refractive index matches identical to this glass, so there's little to no refraction at the surface here. And what this means is we now collect many more rays of light coming off your sample. So your image is now a lot brighter in the microscope, but you also have more light to do that interference and improve your resolution into the back of your microscope. Okay? And you can see this cone of light that we're now accepting into the objective is much bigger, so much higher numerical aperture. Cool. So just to show you how this can affect your imaging, this is an example here. These are just theoretical point spread functions. I think this was done with green light as well, so we're 550 nanometers. So this is an XY, and this is the Axial and XC. And this is for a numerical aperture of 0.1. This is what a little spot of light would look like when it gets to your detector. If you go down to 0.5, you can see that gets bigger. And then if you go down to something like 0.15, which is sometimes seen like a 5x objective, you can see how dramatically larger it is. The other thing that you want to keep in mind too is that this blur or this point spread is a lot worse in the axial dimension than it is in x and y. And that's mainly because this now depends on the square of your numerical aperture as opposed to just being okay. So the last thing that I want to touch on is just the effect of pixel size and position. So everything that I told you up until that point is physics. It's laws of physics, and you can't get around it. That's just the way it is. The exception of super resolution, which we're not talking about today. But what also matters is pixel size. So if I'm going to put up an image here, it's going to be 26 by 12 pixels. Can anybody tell me what that is? If you've seen Jeff Whitman do this before, don't answer. Or if you've seen me do this before, don't answer. All right, so obviously this is really blurry. So this is what happens if you have an image that you're taking on your microscope, where you have a microscope that has a really high resolution, but you don't put enough pixels in there. Okay? So if we double it, the image gets a little bit better. I think you know what it is. You can yell it out. Yeah, it's a zebra. You can see it's still really pixelated, so we want to keep adding some more pixels here. But eventually, at some point, you're not going to notice a difference anymore. So there's not really much of a difference there. Okay? So you can also put in too many pixels. You can put in useless pixels. And that means that you're oftentimes doing photo bleaching or photo damage to your sample unnecessarily. So there's something called the Nyquist sampling theorem. This actually came more from the electronic side of things. But the idea is that whatever amount of resolution that you have, whatever your unit of resolution is, you want to take two samples within that unit. Okay? So here's an example of some images that I took of some microtubules and some cells. And along this dotted line, I've just done an intensity plot underneath here. Okay? So this is just going pixel by pixel with intensity along this line. This one was sampled at a little less than one sample per unit of resolution. This one was done right at 2 samples per unit of resolution, and this one was oversampled at 3.2 units. And so if you look at these plots, what you can see is in the one that's correctly sampled, you can see within these red boxes we have 2 peaks here. Okay? 2 peaks. But in the one that's undersampled, you can't see those 2 peaks. You can see something going on there, but if you actually looked at the pixels, you'd never be able to tell the difference. Okay? And then in our oversampled version, you can see we don't get any new information that we didn't already have before. So this is analogous to a point scanning confocal microscope. And in this situation, you want to make sure that your pixel size is about 2.3 times smaller than your unit of resolution. All of our microscopes will actually calculate this for you, so you don't have to do the math in your head. But if you do that lambda over 2NA calculation for your specific sample, you want to again divide that by 2.3, and that tells you what your pixel size should be. This gets a little bit different for a camera. The reason for that is we have square pixels. And so if you have a sample lying in this direction, each one of these pixels comprises half of that. If you have one lying this way, you can see that the amount of, say these are microtubules, the amount of microtubule in each pixel is actually bigger. So we just separate those out. So here the 2.3 calculation doesn't really work. What you actually want to do is use a 3. So whatever your unit of resolution is, divide that by 3 to get what your pixel size should be. Now, with a microscope with a camera, you don't have as much control over this because obviously your camera comes with a certain pixel size. You can't really change that. The one thing you can do is by changing the magnification of the objective that you're using. Okay? And the other thing too is sometimes some microscopes will have an additional magnifying lens inside the microscope that's called an optivar that will allow you to, say, turn a 10x objective into a 16x. But if you get these pixels just right, you're going to get a nice image. If If you get them too big, things are going to be pixelated. If you start making them too small, you actually lose a lot of light. Your image starts to get dimmer. So you also want to avoid that. Okay, so that's all I'm going to talk about today. I just want to show you what we actually missed. So in the light microscope, we talked about some of the basic components, but like I said, I didn't talk about condensers or anything like that. We talked a little bit of physics of light, but we never got into quantum mechanics, which is probably a good thing. We did talk about how an image is formed and what affects image quality. We didn't talk at all about how you create contrast with things like phase contrast. Resolution limit, we covered this pretty well. We didn't talk about super resolution interface. We didn't talk about fluorescence at all. Wendy Salmon did help us out last year, and we will revisit this at some point. And optical sectioning, if you show up in 2 more weeks from now, Sven is going to take us all through optical sectioning. So the one last thing that I will say is there's some fantastic courses that do go through all of these different points in very much detail. A lot of them happen at MDL throughout the summer, so they're actually just wrapping up right now. But if you can talk to your PI and send me one of these, they're phenomenal. And we have some of them listed on the website there. All right, great. So that's it. We'll see you in 2 weeks.